Hi, today I'll be talking about applications of intense mid-infrared laser plasma interactions. And first, I'd like to acknowledge all the many coworkers and colleagues that worked with me in graduate school, and then particularly my advisor, Howard Milchberg. At the bottom, I'll also point out a lot of funding agencies that supported this work, but particularly the SSGF, and all the support that they've provided me over the last 4 years. So digging into that title, I want to first break it up and say what are laser plasma applications we might care about, and then why do we care about the mid-infrared. So intense laser pulses are generally made by taking a modest amount of energy and putting it into an extremely short pulse, which then, with this high power and focus to a small area, high intensity, can lead to very interesting things like coherent terahertz and high harmonics X-ray pulses that can't be made through normal laser methods. Nonlinear self-guiding, where a laser pulse will guide itself through air or other media, just through its nonlinear action with the medium. And then things like laser plasma acceleration, ion acceleration, and strong EUV and X-ray sources, either coherent or incoherent, that come from the really strong interactions of these laser pulses with plasma or metals and other materials. I'll notice particularly that those last two have been used for high energy density physics backlighting or other experiments to probe high energy density materials at the national labs. So then why would we care about the mid-infrared? Well, the entire field of intense laser pulses is dominated by near-infrared lasers, simply because those are the easiest to build with the laser materials and laser gain media that we have. But going to longer wavelengths, you get different parameters for laser plasma interactions that scale very favorably. So the first is just simply the cycle time in between two successive peaks of the laser pulse. Are going to scale with wavelength, which might be interesting if you're looking for nonlinear effects within a wavelength. Next is what's called the Ponder motive energy or cycle average kinetic energy. And this we can think of if there's an electron that's in the field of a laser, in an intense field. For a given intensity, this corresponds to a single value of the electric field that we'll see, and will start to accelerate. However, for a longer wavelength, you also have a longer amount of time, because it's a lower frequency laser, before the electric field will turn around and start accelerating the electron the other way. Because your energy goes up with nonlinear with acceleration, you actually get a lambda squared here, where you'll get remarkably higher energies for the same intensity at longer wavelengths. Next, you have what's the single photon energy. So a single photon or packet of light is going to have an energy that goes as 1 over lambda. And that means that if here I've shown again an atomic potential, if an electron needs to get kicked up out of the atomic potential with a certain amount of energy, for multi-photon ionization, where many photons are absorbed at once, it's going to take a lot more near-infrared photons to do that compared to the not more mid-infrared photons than in a near-infrared. Next is the critical plasma density, which is a very essential parameter in these laser plasma interactions, because a plasma of a certain density has a characteristic frequency of response. And if a laser of the same frequency interacts with it, you get highly nonlinear interactions, lots of absorption. And if the critical density is higher than the laser density is higher than the critical density, a laser pulse will no longer be able to propagate through the material. This critical density goes as 1 over lambda squared, which means that it's actually a lot easier to create critical density plasmas in the mid-infrared. And then finally, there's the critical power for self-focusing. This is when a beam is so intense that it starts to create its own lens just by its interaction with the material, and it starts to self-focus and collapse into a tight filament. And this critical power, at least in air, goes as lambda squared. So I will return to all of these throughout the power of this presentation and talk about them. But I also want to point out that while each of these might be understood on their own, if multiple parameters are changing at once as we go to longer wavelengths, we can get some really interesting effects and new regimes that I'll talk about. So then, as I said, near infrared is the dominant laser type in our field. But at the University of Maryland, we have a cutting-edge new mid-infrared laser system. It packs, again, 25 millijoules, not very much energy, but into an extremely short pulse of 80 femtoseconds. And that's enough to have a peak power of 0.3 terawatts, where a terawatt is 10 to the 12 watts. Now, this is a painful system. It's cutting edge and it behaves like it, but it was worth it for the effects that we were able to see in our experiments. I'll also note that because these systems work by taking a short pulse, stretching it out to something that's much longer, amplifying, and then recompressing the pulse. In our experiments, we had a chirped 70 picosecond pulse, so a much longer pulse. And I'll come back to what chirped means later on, that allowed us to do some interesting work. So then with that introduction, I'll go on to the three main experiments that I did during my graduate studies. Talk a little bit about each. First, laser wakefield acceleration with these laser pulses, then doing really low plasma density measurements with avalanche ionization, both for remote detection of radiation, and then some ionization measurements, which bleeds into my last topic I'll discuss, looking at self-guiding of intense mid-infrared and long-wave IR pulses. So first up, what are laser wakefield accelerators? Why they're interesting? Well, when you have a really intense, high intensity beam inside a plasma, if it's so intense, it will start to blow the electrons out of the way. The electric field is so high, they just scatter, and you end up with these very strong plasma waves, which can have extremely high electric fields. If you put an electron inside these fields that can coast along and be accelerated, and you can think of taking something like SLAC, which is multi-kilometers long, and shrinking it down into something that's 30 centimeters. However, you need really high energy lasers for these, 100 terawatts to petawatt lasers. So these are really big lasers. So looking at the laser in our lab, how could you do this with something that's more around 1 terawatt? Well, one way is there's not just the interaction where you blow the electrons out of the way. There's also something called self-focusing. And that's because when you focus a laser pulse into a plasma, you'll start to see a nonlinear refractive index. And that's because the normal index of refraction depends on your plasma density. But then as electrons start moving very quickly in the laser field, they'll get a relativistic downshift in their density. And so you end up with an index of refraction that's higher for higher intensities. Now, if you have a normal pulse that looks like this, where it's higher intensity on axis than at the edge, that looks, for all my optics people in the audience, looks like a positive lens where the beam lags in the center and starts to self-focus. Now, when you put diffraction and the self-focusing together, you end up with a critical power that depends on the plasma density and how big it is in comparison to the critical density, which, as I mentioned before, goes as 1 over lambda squared. So if we look at the numbers here, in the near infrared, around 1 micron, critical density is actually really high. It's kind of in this awkward space between gas and solid densities. But in the mid-infrared, it's much easier to get to. It's right around normal, maybe slightly higher than gas densities. And so by using this, we can get self-focusing to the high intensities you need for laser wakefield acceleration. So I'll note that our laser demonstrated this a couple years ago with the near-infrared laser by using extremely high density gas jets that were cryogenically cooled. Here we did a follow-up experiment where we used just a normal room temperature gas jet and we're able to see the same behavior, getting self-focusing in this high density or a high fraction of critical density gas jet, and then measuring the electron acceleration that came out of this that were 2 to 10 MeV electrons in just a couple hundred microns of acceleration distance. I don't have much more time to talk about this today, but I'll note our publication on this from 2018. So next we did measurements of really low electron densities with avalanche ionization. And so first off, what is avalanche ionization? Probably haven't heard of it before. In avalanche ionization, you start with a single electron that wiggles in your intense laser field. And as it's going back and forth, every once in a while, hit another molecule, and that allows it to dephase from the laser field and through many collisions actually gain energy. It's called collisional heating. Eventually, it gains enough energy that it can ionize one of these molecules, and you end up with 2 electrons. which then start repeating this process over again. You go 2, 4, 8, and continue, and you get exponential growth, so that you start from one single electron and you can end up with a bright plasma spark where you've ionized everything in the air around that initial electron. For those who are familiar with photomultiplier tubes, we often say that this is single photon, single electron sensitivities, similar to a PMT, where there you get electron amplification each time an electron scatters off of these really high intensity electrodes. Now I'll note that these pulses for avalanche ionization need to be a little bit longer, at least picosecond, and lucky for us, we had a picosecond laser. But during just a picosecond laser, you'll get electron motion limited by diffusion. And that's because as these electrons are bouncing around, creating more electrons, this all happens locally and they don't have very much time to spread out. And so you'll end up for a picosecond pulse with usually micron-sized little sparks of plasma that came from an initial electron. And that's really powerful because you can pinpoint in air a single electron just by using this technique. So why hasn't this been used before? Well, we come back to the mid-infrared. The early experiments with avalanche ionization used near-infrared lasers. And because you need a high intensity to drive avalanche, you'll also get a lot of multi-photon ionization I talked about before. So if you're looking for one electron in the air, your laser ends up making 1 million electrons at that intensity and then avalanches those, and you never see that one electron. However, as you go to longer wavelengths, there's less multi-photon ionization, and because the Ponner motive or cycle average kinetic energy is higher, you get more avalanche ionization. And that's shown schematically in this little picture here, where I have these two X's have the same amount of avalanche growth, but because of the difference in intensity and the difference in photon energy, they differ in their multi-photon or unwanted ionization rate by a factor of 10 to the 20 or 20 orders of magnitude. So you gain a lot by going to the mid-infrared. So how did we use this as practically in our lab? By focusing a laser down where there are a couple of electrons, we create a region represented by this little red outline here where the avalanche will happen, and individual electrons lead to these individual sparks that we've imaged here. So we're able to measure extremely low plasma density or electron densities just by imaging, but then we also were able to do some timing measurements because, as I said before, we have a chirped pulse, and that means that at different times during the pulse you have different wavelengths. So by looking at the spectrum that gets scattered off of these little plasma breakdowns, we could figure out how long it took for these breakdowns to happen. So the first thing that we wanted to do with this, and actually what we were funded to do, was look at a remote radiation detection. And this is because normal radiation methods like a Geiger counter look for alpha, beta, and gamma particles. As you move far away from a radioactive source, the flux of these particles goes down as 1 over r squared, in addition to any linear absorption. And so it gets really hard to measure anything past 100 meters or so. However, because these particles are depositing energy in air, they create extra free electrons, which we might be able to detect with avalanche ionization by focusing a laser from far away and looking for these sparks. And these are only 10 to the 4 to 10 to the 7 electrons or ions per cubic centimeter right next to a radioactive source. This is a little inset from measurements we did next to an alpha source. So it's very low, you wouldn't be able to see it directly, but we could be able to see it with avalanche ionization. So we set up an experiment to do exactly that. Here's the alpha source that we had. We scanned it close or far from a little focus right here. And we set up our laser to focus from 1 meter, so kind of quasi standoff, and then looked at our backscatter spectrum for timing, and then also things like fluorescence. And what we saw is that we could count these individual electrons to determine densities from 10 to the 3rd down up to 10 to the 7 per cubic centimeter, but also that as we moved this source around, we could see the changes in breakdown timing that told us how strong the radiation field was. So this is kind of a high-level overview of our results. There's more details in these 2 papers from 2019, but kind of I'll give the big overview of it was that we tried this first in the near infrared. That was the first project I did during my graduate studies, and it failed for all the reasons I talked about before. But this is from the day that we first got it working. You can see that this is actually a radioactive flow source where it's putting out air that's been partially ionized. And we can see that the breakdowns only happen when the radioactive sources, the air that's passed through the radioactive sources is going through the focus. So this was pretty exciting for us. So last, I'll touch on some experiments doing with self-guiding. They'll still involve avalanche ionization, but they have a different motivation. So I talked before about self-focusing and filamentation happening in plasma, but the same thing happens in air for a slightly different reason. So air has an index of refraction just from electrons moving around when in the presence of a laser field. When that laser field is really intense, the electrons start being pulled in weird ways, and they'll end up having an intensity-dependent index of refraction again. Once again, this gives you a higher intensity on axis, is the same thing as a higher index of refraction on index axis, and you end up with this self-focusing. And again, a critical power. This critical power now is dependent on lambda squared. Now, a beam that is above this critical power will start to self-focus until something stops it. In this case, that something is ionization of the air, which will tend to defocus the beam. Now here I've shown that if you have a longer wavelength, then you can have a self-focusing and collapse of a shorter wavelength of the same power. But what people are really interested, those who might want to use this to say hit a target at range, is to put more power into a beam and travel that in a single filament before it starts to break up because of modulational instabilities in the plasma. And so by going to longer wavelengths, you can get more power before these instabilities kick in. So a couple of years ago, there was a group out of UCLA and with them, Brookhaven National Lab, that showed that you could do this with a 1 terawatt, about 1 terawatt CO2 laser pulse, cutting edge for these long wavelength laser pulses. But they saw filamentation and self-guiding, but they saw that it was happening at 1 terawatt per centimeter squared, which is really, really low. You don't expect any ionization, so they didn't know what was stopping the beam from self-focusing further. After kicking around, they came up with a theory that said, oh, there's some new ionization mechanism that will cause extra plasma to form, that will avalanche and stop the beam. So this would be really low level ionization and hard to measure. Well, we just realized we had just done experiments with avalanche ionization, and we could measure really low ionizations. So we set up a second experiment where we focused ultrashort pulses, either 1 micron or 4 micron, into a gas cell, and then used the rest of our 4 micron pulse to avalanche any electrons that were released by the first pulse and measure that any low level ionization. So by doing this, once again, we were able to measure individual. We did a couple different geometries. So either the beams were collinear or perpendicular, so you could get different volumes and as a result, different ionization probabilities or yield. So here I show one plot where we were measuring over different intensities of our pump pulse. We could get yield of 10 to the negative 16 up to 10 to the negative 11. So 1 out of every 10 of the 16 atoms being ionized. Putting all of this together, also with some timing-based measurements, we saw that we measured all the way from 10 to the negative 16 up to the negative 2, which is an extreme range. It's very hard to get plasma density measurements over even 2 orders of magnitude with normal methods. And comparing here with this yellow line, we saw that our measurements matched up really well with normal ionization theory. So there was nothing to see there. We did see some different behavior at very low intensities, but after doing a couple different measurements at different wavelengths, we realized that these were contaminants in aerosols. So things like little water droplets or maybe hydrocarbons that were left over in our gas cell. So what was going on? What could still be causing this avalanche? Well, one thing that we noticed that there were these contaminants, so maybe they could be having an effect, but we also saw that aerosol, if there was any dust in our system, it would lead to breakdowns. And so we came up with an avalanche propagation model that included everything that we knew about avalanche, as well as effective index of refraction from these discrete plasma breakdowns, and put them together. And what we came up with was published just this last year in 2020. We found that if you have aerosols, things like dust floating around in your air, that leads to much faster avalanche that can arrest the beam and allow it to self-channel at these very low intensities in a large beam. If you don't have those, you'll get collapsed to kind of what's normal filamentation and very sub-millimeter filaments. And then I've shown here, just again in C, comparing with the near infrared, here you're able to get much more power before the beam starts to break up into many filaments. So that is an overview of the experiments that I've done in grad school. And I hope, even though I couldn't dig into the details of each, they give you a high-level overview of why the mid-infrared is interesting for laser plasma interactions. And I want to thank, again, everyone who's helped me in my research group, in my family, and the support that they've given me, the funding agencies, and then once again, SSGF for providing this fantastic opportunity to be a part of this fellowship and many opportunities to learn and grow at the labs and at these program reviews. And I hope to be able to see some of you again soon and answer your questions when this review happens. Thanks.